Hello, this video is the second video in the topic of gravitational fields. Last video was on Newton's law, and this one is on understanding how we measure the gravitational fields. So what is a gravitational field? So any kind of field is always talking about an area of influence. So if you have mass, so an imaginary sphere around this mass, which is the area of its influence, so where the other bodies can experience the force or energy or can have some kind of energy. So this area is field. Now the field is made visible by drawing lines of force. So for the mass, the lines of force, if I draw like this towards the mass and along the radial lines, this is called radial field because the field is along the radial lines of this sphere around this M. So what does this line represent? They just represents the field. Now field is measured in two ways. One we call as gravitational field strength, another is called as potential. So both of them are a way to measure the field or gravitational field. So the gravitational field strength is a vector method. So this is a vector method. So gravitational field strength sometimes noted by E and sometimes denoted by small g. This is a vector. And this other one, the potential, which is denoted by capital V, is a scalar. Both of them are used to measure the strength of the field. So we're going to first start with the gravitational field strength. So gravitational field strength, E, which is a vector, it is measured by measuring force experienced by some mass which is kept in the gravitational field. So what we do is, suppose if I have a gravitational field, okay, I'm just drawing the field lines. So this is a gravitational field, and in this gravitational field, if we keep a mass small m, so I'm just taking a different color, so let's say my small mass m is here. So what force this m experiences, by measuring that force and then dividing by this mass itself, we measure the field strength. So that's the way. So the unit is Newton per kg. Nature, it's a vector whose value is given by F over m, and its direction is towards the mass. Okay, so direction is towards the mass. Which mass? Not the small m, is the mass which is creating the gravitational field. Okay, so for example, creating the field. So suppose, for example, the capital M here is creating this gravitational field. So this is towards the mass. So these lines are nothing but the direction of gravitational field strength. Okay. The third point is, what I want to make here is, if I replace my force with gmm over r square, I get the formula for field as this, field strength as gm over r square. So this is the formula that comes from Newton's law. Okay, let's just understand it more. So suppose, this is what I mean to say. So suppose if I have a mass capital M at distance r from it, the value of gravitational field strength is gm over r square. And what's the direction? Because it's a vector, so you will have to show direction all the times. So direction is always towards the mass. So the direction is towards this mass. Now suppose if I want to find gravitational field strength at this point here, it's the same distance r. The distance is not changing, so the value will not change. Gm over r square. G is not changing, the mass m is not changing, r is not changing, but the direction would be in upward direction. So this is the direction. Say, wherever you go, all around the mass m, wherever you go, so suppose if I come here, same distance r, so the E will be gm over r square. The value is same all around it, only now the direction is towards this. So can you see how the direction is changing? So that's it. That's your gravitational field strength. Now let's just do some basic recall question. Pause and try to do it yourself. Okay, and if you've done it, let's just check the answers. Now I'm just going to explain you the last part here, just going back. So why is the gravitational field inside a uniform spherical shell 0? So I'm just drawing here. So see, this is a shell. Okay, imagine this shell is like a chocolate egg, and a chocolate egg which is completely empty inside, and the mass is only on its circumference. So everywhere inside it, the field would cancel out because of all other mass, and the resultant field would be 0. So because the contribution from all parts of the shell cancel out exactly at any point inside. So if you consider, let's just try and do it somewhere here. So this is my shell. So if I want to calculate the gravitational field strength at this point, it's fine. This is because of this mass, the field strength is towards, and then because of this mass here, the field strength will be here. Because of this mass, the field strength will be here, and so on. All the field strengths, because of different masses, would cancel each other out, and the resultant will be 0 at any point. So field inside a shell is always 0. Spherical shell, it has to be spherical. If it is of any other shape, if we make the chocolate egg a square in shape, the field inside will not be 0, because then it will not be cancelling each other. All right, now this is the scalar method to measure field strength. Okay, how strong or weak a field is, a scalar method to do that. Sometimes we need a scalar method. Now, defined as energy, so I'm just using a symbol U for energy. That's a symbol used for potential energy per unit mass. So that's the potential. Scalar unit is then joules per kg. That one was Newton per kg. This is joules per kg. Now, so if I have a mass m and I want to find potential at distance r from here, the value of potential would be same because it depends only on the distance. It does not depend on the mass. But what's the value? I'm going to give you the formula right away. I'm going to explain you why this negative sign. So minus gm over r. So minus gm over r minus gm over r. No direction because it's a scalar. So everywhere around this mass m, potential is same. Now, why does this negative sign? Let's just understand what's the meaning of potential. All right, let's say this is your Earth, okay? Remember, again, we did it in the last video, that if it's a sphere, the mass is assumed to be at the center. So this is this Earth. So if a body is at point A, at point B, where does it have more potential energy? At A, clearly potential energy at A is more than potential energy at B. So as it comes closer to Earth, what happens to its potential energy? So potential energy decreases. Okay, so closest to the body, the potential energy is smallest, and that smallest potential energy is given a negative sign. So the potential energy closest is minimum. So potential energy at C is minimum, and potential energy at A is maximum. So what we assume is if you keep taking it higher and higher and higher, and let's say you go to infinity. So at infinity, the potential energy is highest, and that highest value is 0. Yes, I know it is confusing. It is very confusing that we're taking the highest value as 0. Now, if we take highest value as infinity, we cannot work with it. We cannot work with infinity. Adding infinity to something would make it infinity again. So what physicists did is they took the highest value as 0 and then the minimum value as negative. So the potential at, say if I take a mass m here, at distance r, potential is at point A. So the potential at point A is minus gm by r. And what is the potential at infinity? Let's say the infinity is here. So this is a symbol for infinity if you don't know. I know you know, but just in case. So the potential at infinity is 0. It is because it is easier to handle 0 than to handle infinity. So obviously negative is smaller. So as you come closer to point A, the potential is decreases and becomes negative. So potential comes from potential energy. Higher position, higher gravitational potential, highest gravitational potential is 0. Okay, I'm just going to write here. So higher position, this will help you to remember. Higher position is higher potential energy. That one is clear. Okay, so I'm going to write potential energy, so which is equal to higher potential, because potential is defined as potential energy per unit mass, and highest possible potential is zero. Yeah, that's it. Okay, so highest possible potential is 0, is equal to, so I'll just write potential is equal to 0. Okay, just if your mind is deceiving you, it's not ready to accept, just tell yourself, if I want to add 2 plus infinity, it is going to give me infinity. So this 2 will not have any relevance. So 3 plus infinity is infinity. So because dealing with infinity is difficult, we deal with instant 0. It is up to us. We are defining all these numbers, all these equations to understand. So it was up to us to define 0 or infinity. So this is what we decided then as physicists, that okay, fine, we'll take highest as 0, and then as we come closer, it is becoming negative. All right. So to understand what is potential energy per unit mass. So obviously then potential energy, gravitational potential energy, is mass times potential. And we saw that potential is defined as minus g capital M over r. Remember, now the field is produced by which mass? The mass which is in the equation for V. So my potential energy then becomes minus g small m capital M divided by r. So any two masses. So the field is of capital M. If you keep another mass here, the distance between them is r. The potential energy is minus g m m over r. You will be given this equation, but you need to come up with this on your own. All right. So potential energy, as you can see, is negative. Now, what is the significance of negative here? Whenever you have potential energy of any system, if it is negative, that shows attractive force. So this helps the physicist to find out the relation between field and forces. So if the potential energy is negative, the system is a bound system. So if you're launching a satellite, okay, the satellite around the earth is having one energy, which is potential energy, and it, because it's moving around the earth, it will also have kinetic energy. But the total energy of the satellite has to be negative. The Ke plus Pe part should be negative. If it is not negative, the satellite will fly apart. It will escape into the universe. The total energy of any planet around the sun is negative. One, its potential energy, one kinetic energy. Because the total energy is negative, these planets are bound to the sun. Now imagine if someday some planet is hit by some asteroid, or I don't know, whatever, the speed of the planet increases in such a huge amount that its total energy becomes positive. Forget positive, even if it becomes zero, the system, it will not be bound to sun anymore. It will escape into the universe, into the space. So we are all on Earth, right? We are on Earth with whatever speeds we move, whatever speeds the jet planes move, or even supersonic jets, anything moves. So anything that's moving will have kinetic energy. And if it also has this negative potential energy. But if you do the calculation for any body, any speed, you will find that the total energy of all the objects on Earth has to be zero, has to be negative. If it is zero, it escapes. So if you're launching some satellites, or so let's say we are launching some space rockets, we want them to escape the Earth's gravity. What we are looking for is to make their total energy negative. Their kinetic energy should be such amount that it should be equal to the potential energy, so that the total energy becomes zero. The minute the total energy of any bound system becomes zero, it is no more bound. Okay. All right. So now, just to recap, what's required for your exam is the potential energy is negative, all right, between two objects. Gravitational potential is negative. What you remember as mgh, that is a change of potential energy. So if a body here, its potential energy is minus gmm over r. If it moves to this point, its potential energy will be minus gmm over r plus h. So as it moves from surface to some height h, the change of potential energy is mgh. This is what you have been calculating over the years. So you're calculating the change of potential energy. Okay. Now, potential is obviously measuring field strength, and field strength is also measuring field strength. So you have two things to measure the strength of the field. One, the vector method, another is the scalar method. So because they obviously will be related to each other. So gravitational field strength is force over mass, okay, and gravitational potential is potential energy over mass, or potential energy can also be written as work done over mass. Now, what can you write work as? You can write work as force times total some displacement in the direction of radius, and this force times, so this is V, and force divided by mass, it is nothing but E. So we can write E times delta R. So that is the gravitational potential and field strength. Now, some questions again, pause and try to answer them yourself. Once you've done that, mark. Now, only thing is you will have to just remember that potential is negative at the highest at the closest point and is zero at the highest point, infinity. Now, planetary motion is obviously the cause of planetary motion is gravitational force between the sun and its planets. So this gravitational force is the force that provides the centripetal force for the journey in the circular path to the planet. Okay, so if this is the sun and you have a planet here, okay, it's big. This is a horrible diagram. All right, so that's better. So if there's a planet on the circular path, so this is a planet and this is a sun, mass capital M, and the planet has a mass small m, and distance between them is r. So if you take the distance between them as r, the gravitational force is g m over r square, Newton's law of gravitation, and the force on the planet is towards the sun, which is providing it the necessary centripetal force. So this is equals to mv square over r. So larger the gravitational force, larger would be the speed. It can move around the sun. And obviously, once you have the speed, you can calculate the time period of motion. The distance it is traveling is 2 pi r. Of course, if you're considering the orbit to be circular, you do not have elliptical orbit as such. So 2 pi r divided by the speed. That's the time period of the orbit or orbital time period. So larger speed would depend on the larger force. All right, let's just go ahead, pause and do. So if I'm going to just do these ones, so if the gravitational force suddenly disappears, seeing this one, so if this force becomes zero, so what is this force doing is it is kind of changing the direction of this velocity. It comes here. Because of the force, the velocity changes its direction. It comes here, the velocity changes its direction too. Okay, so the force is continuously pointing towards the center, which is the sun. Okay, so the purpose of this force is to change the direction of velocity. So if this force suddenly becomes zero, it's going to keep moving in this direction. There's no force to change its velocity. So it'll keep moving tangential. So if the planet is farther from the sun, if I increase the distance, let's say the sun, planet, another planet, another planet. So larger distance from the sun means force decreases. So if force decreases, the speed of rotation decreases. It moves slowly, so obviously it'll take more time to complete one circle. So the time period of increases, so longer orbital period. So that's your answer. Pause and check. Now this is a question, could be a part of any of your exams. Why a planet in elliptical orbit does not move with constant speed? You go ahead, pause and try to answer it yourself. Why? Explaining, going back to this one, why if it is an elliptical orbit it would not move at constant speed. Obviously, see, so that animation is also talking about the same thing. So if I have a body which is, when it is far away, what happens to the force? Is it less? Yes, larger distance, less force. Force is less, so speed is less. closer, force increases, speed increases. That's it. So it cannot move with a constant speed. Whereas if it is moving in a circular path, it ends up moving with a constant speed because the force is constant. Okay, so this is coming from the Kepler's law, generally that t square is proportional to r cube, where r is the radius. You do not need to remember this, it's just for your understanding. Sometimes the questions would tell you this, and then if you would have heard of it somewhere, it becomes easier for that given question. So it's a radius of the orbit. So as you can see, larger the radius of the orbit, larger is the time period. Right, here you go. So same, pause and do it. Once you've done, mark your answers. Now, geostationary orbits. So geostationary orbits, okay, now as you can see in this small animation, that point on Earth which has this private satellite, wherever that point goes, the satellite goes with it. So that means what? With what speed is the satellite rotating, or what is its time period of rotation? Is it same as that of Earth? Yes. So that's the first point to be understood about this geostationary orbit, is the time period is same as that of Earth. And what is the time period of Earth? That is 24 hours. Second special thing, what do you notice? What is the location of the satellite? It's in the equatorial plane, so this is around the equator. So this is the equator. So that is an important point about a geostationary orbit. So this one is in the equatorial plane, and equatorial plane only. You know, the height of geostationary orbit is, so if once we know that we want this to complete one rotation around the Earth in 24 hours, so we kind of know the time period. So using time period, we can calculate the radius. So it always at a height of around 36,000 kilometers above the surface of Earth, around 36,000, not exact. So now there is a difference. So what's the use of having such a satellite? It is used for weather monitoring. If you want this particular place in Earth, what kind of weather is there for the next 24 hours or for next week, it has to be always above that position. So it's a weather monitoring, TV communication, and all of that. All right, so now another question here. Okay, one, see, the second point, if it is not above the equator, it is not geostationary, because geostationary, we want that satellite to be stationary. Geo means Earth, with respect to the Earth. So it, with respect to this position on Earth, it is always, it looks like it's always above us. So it is stationary with respect to us because it is moving at the same speed with respect to us. So if it is not in equatorial plane, it is not geostationary. Okay, here we go. So correct answers, and that's it. So this is about the field, potential, confusing things about potential, planetary motion, time period of planets around the sun. Please revise through it again and again till your concepts are clear. Do not start solving exam questions till you're completely clear of the topic. So this finishes kind of gravitational field, but I'll be making a next video on Kepler's law. Edexcel doesn't need to do Kepler's law specifically for the exams. For the other students, you can go ahead and watch that video, but till then, keep revising. Well done for watching. Thank you.